All right, we're still in chapter 10 here, and we want to begin talking about phase transitions, okay? Now, remember there's three states of matter that we're just going to be discussing here in the course, solids, liquids, and gases. And we've outlined their characteristics and properties to some extent, especially gases, all right? This slide here shows you the six general phase changes that are possible in the chemistry class. So you can, remember you have three different phases, okay? And you can go from any phase to another phase, even from solid to gas and gas to solid. So vaporization is what we use to describe a phase from liquid to gas. Condensation is a phase change from gas to liquid, okay? Phases and states are the same thing. Fusion is when something melts, so that's when a solid gets transformed to a liquid. Freezing is when you go from a liquid to a solid. And these last two might be less familiar to you. Deposition is when gas changes to a solid. And I'll show you a little video of my car. You can see some frost building up on it. And sublimation is when you go from a solid to a gas. That's most visible maybe with mothballs, which is naphthalene. That substance just disappears and you don't see a puddle forming in the process. Menthol is in cough drops, and it's a solid substance in a pure state, but you can see, you can smell it, so you know that it's changing from a solid to a gas directly. And also in the cold winter night, you might have an ice cube that gradually just disappears, okay? Some snow disappears, a little patch of snow disappears on a cold night just because it's changing directly from a solid to a gas, and it's getting smaller, you can see from day to day. And the reason why is because there's just little water vapor in the air, so it changes directly from a solid to a gas. And you know that's happening because it's not warm enough for it to melt and form liquid water, which then evaporates, okay? We're very, very familiar with frost, and sorry about that noise, but this forms by deposition of water vapor from the Earth's atmosphere to form ice crystals. And sometimes you can see spindly little jagged things that form on surfaces like cars and grass. And I want to show you another interesting feature I've noticed is sometimes you have frost heave. You know, when water freezes, it expands and sometimes forms these very interesting looking structures. The water is pushing out of the ground, and it forms these very interesting rope-shaped, kind of like noodle kind of things. And I just think that's just so fascinating. And that's just ice there, and all of these are just pushing out of the ground, going up like a couple inches here. And I guess there was water underneath, and when it froze, it had nowhere to go, but it expands, so it's just growing. I just find it just quite amazing. Condensation, or when gas changes to liquid, happens, of course, when it rains, like on today, and whenever you have excess water vapor in the atmosphere. So here we're doing some laundry, and the dryer vent is releasing some steam there. And then in the atmosphere, as it cools down higher up, it actually condensates and forms a cloud-like appearance. Now, there are two different types of phase changes, those that absorb heat and those that release heat. So the endothermic phases, remember endothermic means heat is absorbed or heat is put into a test tube or a system, okay? And these are the three phase changes for endothermic processes, all right? And you can do these phase changes with a stove or, you know, a flame or something like that, or even sunlight, for example, okay? So you can melt an ice cube or go from a solid to a liquid. You can evaporate water, which means it goes from liquid water to steam, right? And that's not necessarily the boiling, okay? Boiling occurs at 100 degrees Celsius for water, but here we're just talking about simple evaporation, so it might be a rain puddle after it rains, and then because the ground is hot or the cloud's clear and the sun comes out, it just evaporates slowly, okay? So that does not occur at the boiling point of water. Now, if you're cooking spaghetti or something and you have a pot on the stove, then yes, that's evaporation that occurs at the boiling point. And definitely you can see it's endothermic because you have to put it onto a heated burner for that to occur. Sublimation is when you go from a solid to a gas, and that process also takes energy, okay? You have to heat it up or input heat into the system in order for sublimation to occur. Now, these are the three exothermic phase changes, okay? Exothermic means heat is released, okay? Heat is released. You can cause these transformations to occur by putting something into a freezer, but it's not because you're adding coldness to the test tube that's causing this. Rather, it's the thermal energy in the test tube that's being drawn out by the freezer to cause these phase changes to occur, okay? So you can have steam condenses, right? Steam is a water vapor in the air. You can't see it, and then it gradually forms a liquid form. You can see that on a cold winter day when you blow into the air. You can see your breath, which is steam, condensing to form kind of a cloud, okay? You can also, when you clean your glasses, for example, if you have glasses, you go like that, and then you can see fog build up, okay? So that's a condensation as well. When you open the freezer door, maybe in the summertime to grab an ice cream or something, you can also see condensation occurring as well, okay? And what's happening is moist air outside of the freezer in your kitchen is going into the cold air in the freezer, okay? And it circulates around. And upon the colder temperature, then the water vapor comes out, okay, as a condensation. And it changes into very small water droplets. It's liquid water droplets, okay? So whenever you look at a cloud, certain clouds are ice, but most of the clouds, like cumulus clouds, things like that, are water, liquid water, okay? So when you look at a cloud, it's kind of like a white color, okay? When you see your breath on a cold winter day, or you see that fog formation in a cold freezer, you're actually looking at very small water droplets, okay? So those are all examples of condensation. Water freezing is when you go from liquid to a solid. And of course, we do that in the freezer, right? We fill up an ice cube tray with liquid water, we put it into the freezer, and it forms ice, okay? For that to happen, there's all these pumps and different mechanisms in your freezer to pull away the heat from the liquid water in order to slow the molecular motion down enough that it locks into place in that hexagonal crystalline structure we talked about before, okay? Deposition is when you go from a gas to a solid, and I talked about this when I showed you pictures of my car that was frosted over. Whenever you have dew occurring below the freezing point of water, which is 0 degrees Celsius, you're going to have frost formation, okay? So whenever you have frost occurring, that's a deposition, okay? We know that there's not liquid water falling onto the surface of my car and then freezing because we don't see little bubbles or little round circles of ice. What we see are jagged snow crystals, okay, that look like snowflakes kind of in a way. And that must have occurred by gas molecules of water in the air, called steam, hitting the car. And then because the car was sufficiently cold in temperature, it immediately changed into a solid state, okay? And then the crystals grew in a very intricate pattern, okay? Much different than a liquid water droplet. There's this term introduced in the OpenStax chemistry book and in chemistry in general, and at this point we want to talk about dynamic equilibrium, okay? Whenever you have water, this is a complicated solution of mouthwash, I guess, but in the gas phase here, we have water molecules floating in the gas phase, and we have water molecules down here in the solution that are in the liquid or aqueous phase, okay? So liquid water and gaseous water. And there's a dynamic equilibrium, okay? For every water molecule that vaporizes and changes from a liquid water molecule to a gaseous water molecule, there's going to be one water molecule that's in the gas that goes to form liquid water molecules, okay? So you have billions and billions of trillions of water molecules evaporating and billions and trillions of water molecules condensing, okay? And there's this dynamic equilibrium occurring. Now we know that if we set this on the tabletop, it doesn't build up pressure and explode. We know that it doesn't develop a vacuum and get all crumpled up or something like that, okay? So it maintains the constant pressure inside of here. All right. Let me show you this animation here that might help you view it not on such a large macroscopic view, but on a microscopic view. Okay, so what we're looking at here is a little box. Okay, there's a cube, and we have some water molecules, H2O molecules in this box. Okay, and what happens is there's a little bit of gravity here that's turned on. So if I rotate the box one way, they all kind of run down to the lowest point in the box because it's a liquid, right? Liquids flow downhill. And what you'll notice is that there's a tremendous amount of molecular motion. There's water molecules in constant motion. They're vibrating, okay? The oxygen-hydrogen bond is vibrating. They're vibrating in this way as well. They're rotating, and then they're translating through space. So we have all 3 degrees of molecular freedom in this liquid water state, okay? Now, if we increase the temperature here with this slider bar a little bit, we can start to see that the molecular motion is more rapid, okay? So remember again that if you increase the temperature of something, the average kinetic energy of the molecules in the sample is going to increase. And if we rotate this box around, I guess maybe like this, you can see how most of the molecules are falling down into this portion of the box. Maybe I'll rotate it a little bit like this. Most of the molecules are falling down to this corner of the box, but there are some molecules like this one up here on the upper left that are being kicked off and flying, okay? So these represent gaseous water molecules that aren't in the bulk liquid, but off onto the side, okay? So every once in a while, a water molecule is ejected, it comes back, another one's ejected, and it comes back. And so on average, I mean, maybe there's 4 or 5 different water molecules here in the gas phase, okay? So this represents dynamic equilibrium of vaporization, molecules changing from liquid to a gas, and condensation, molecules changing from a gas to a liquid. If I increase the temperature more, we will see that the kinetic energy is sufficient so that the molecules have so much energy to break those hydrogen bonds. And now they are roughly distributing themselves freely and randomly throughout the whole volume of space here. And that would represent the gas phase, okay? So if we put it up all the way on the top, hopefully it doesn't crash my computer, these molecules are completely random, they're spread apart, and that would be 100% gas, okay? On the opposite extreme, we have 100% liquid, but in between, you have a mixture of liquid water and gaseous water, okay? And air is naturally humid, not so much here in the wintertime when I'm making this video, but there's water vapor in the atmosphere and there's liquid water around. Different ponds and rivers and streams and things like that. And in a closed water bottle, there is going to be dynamic equilibrium, okay? Have a better view of what dynamic equilibrium is. And this is important when we talk about chemical reactions in the future, which rely on concentration, okay? Now, vapor pressure is the partial pressure of water vapor or water, or steam in a container at a certain temperature, okay? So we know, for example, that the Earth's atmosphere is made of about 80% nitrogen and about 20% oxygen. We'll forget about argon and carbon dioxide. But there's also water vapor here, okay? So the pressure of water, we're not talking about is just the pressure in this room. We're talking about the partial pressure of water vapor in this container. Now, at this temperature, it's going to be saturated. It's going to be 100% humid, okay, in this container right here, because it's been sitting there at equilibrium for such a long time. But keep in mind that vapor pressure is going to depend on only two things: the intermolecular force of the liquid, okay? So if we're talking about water, water is highly polar, it has hydrogen bonding, and so since its intermolecular forces are so strong and water molecules are so tightly held together in the liquid state, it's going to require a very high temperature to create a sufficient pressure within this bottle. Gasoline, on the other hand, is CH18, and that's a nonpolar molecule that does not have hydrogen bonding and it does not have dipole-dipole forces. So in gasoline, the only thing holding gasoline together in a liquid are London dispersion forces. And if you've ever had the occasion of maybe chainsawing some trees in the summer or mowing a lawn and you leave your gas can out in the open in direct sunlight, and then after you do your yard work and you come back and you look at your gasoline can, it's bulging out and it looks like it's bubbled up and it's about ready to explode or something. And the reason why is because the sun has warmed up the gasoline on the inside. It has caused these very loosely held gasoline molecules to evaporate and create more gas phase and greater vapor pressure. And the gasoline tank can break, you know, if it's too hot and it's in the hot sun. Okay, it can burst the container. Whereas if you put this out into the hot summer sun, nothing would really happen. It would just look steamy inside or something, but it wouldn't break the bottle. It wouldn't be bulging out. Okay? So higher intermolecular forces of the liquid are going to have lower vapor pressure, and lower intermolecular force liquids are going to have higher vapor pressure. An extreme would be oxygen or nitrogen. Oxygen and nitrogen are both nonpolar molecules. They are such a small molar mass and surface area that they have almost no London dispersion forces, and definitely at room temperature there's no forces holding oxygen together. It's a gas at room temperature. So I don't know what the boiling point of nitrogen is. I think it's 77 Kelvin, which is what, negative 176 Celsius I think it is. And oxygen, I don't know the number offhand, okay? The other thing that will vary the vapor pressure in a liquid is definitely going to be the temperature, okay? So if you put this out into the hot sun, there's going to be more gas vapor in here compared to a cold winter day, okay? So higher temperature, higher vapor pressure, lower temperature, lower vapor pressure. The vapor pressure in this container does not depend on the size of the container. If this was twice the volume, it would still be the same pressure. If I had only one drop of this mouthwash solution in this bottle, the vapor pressure would be exactly the same, okay? It does not depend on how much liquid you have, as long as you have sufficient material in the gas phase and the liquid phase to establish conditions of dynamic equilibrium. It really doesn't matter about all this liquid on the bottom, okay? So it doesn't depend on the size of the container, how much liquid you have in there, how much gas you have in there. As long as it's closed and it's at a certain temperature and you know what that liquid is, it's going to have a certain vapor pressure, and we could calculate that or determine that if we needed to. Okay? So I hope that helps you understand vapor pressure, dynamic equilibrium, and phase transitions a little bit better.